perhaps it is visible to you, and this is what we were discussing in the previous class, the performance of power system, how this can be actually measured and how this can be assessed. We talked about the necessity of voltage control and frequency control. There are other issues like security of the system and economy also. So those things, economy, as I told you, will be taken care of partly in the other half of the subject. Security obviously will not be included here because it involves so many other things. These will be, the security aspect will be covered in the power paper in the fourth year class. Okay. So now for today's content paragraph, this was discussed how why frequency changes. Uh, Main reason is the unbalance between the active power input and active power output of the generator. I've explained. I hope you could also follow this. And if you have any question in mind, anybody, please ask me. I shall try to explain it. And also, I have discussed the voltage control. Why voltage control is necessary? Why voltage drops? Which part of the power is more responsible for voltage drop? And it was shown that reactive power, that is mostly responsible. But this part also I have discussed that when active and reactive power is being delivered by the generator and it is received by the load center, then it can be shown that it is the reactive power flowing from the generator end to the load end that is more responsible for the voltage drop, and phase angle difference is basically created by the active power portion. Okay, so this also was discussed. Now the observation part here, whatever we have discussed in our previous lecture, from that we can observe these things. The first thing is that a change in P, active power, affects the perpendicular component of the voltage drop. You see here. When you refer to this phasor diagram, you see that a change in P, this part is responsible for this part, this perpendicular portion, P by V1x, this is responsible. And for this portion, Q by V1x, this is responsible. That means in phase component of the voltage drop, that is created by the reactive power. That's why the reactive power is more responsible for the magnitude drop, and quadrature component of the voltage drop, that is being created by the active power. That is why phase angle difference is mainly created by this active power part. Okay, so we can say that change in active power demand has little effect on the magnitude of V2. That means voltage magnitude will not be disturbed much because of the flow of active power. If you increase or decrease the magnitude of power that is being transmitted, power means active power that is being transmitted through a transmission line, the magnitude of voltage will not be affected much. Rather, the phase will be affected. Okay, so reversely also you can say that by changing the phase angle difference, you can make arrangement for the flow of more or less amount of active power. Okay, and the second observation is a change in Q affects the in phase component of voltage drop that I have shown. That means in phase component of the voltage drop, that is mostly created by the reactive part. Why I am saying mostly? Because we have ignored the resistance of the system, because the high voltage transmission system resistance is very small compared to the inductive reactance, and we have neglected the resistance. That's why I told you that for this discussion, what we are making in this portion of the subject, it is valid for the high voltage part of the power system. We are talking about power transmission. Power transmission always takes part, always actually is done at high voltage. So this is valid for high voltage. If you go for the low voltage part, the distribution part, there you see that both resistance and reactance, line resistance and reactance, component resistance and reactance, both are equally responsible. So this discussion is valid for the transmission level only. Okay. So change in voltage magnitude is mainly caused by the reactive power. So active power causes phase angle change, reactive power causes voltage magnitude change. This has to be kept in mind because this will be actually required on many occasions if you study power system. That means in the incoming courses this also will be required. So what are the inferences we can make? Active power flow through lines can be changed by controlling the voltage phase angle. That means since active power flow creates phase angle difference, therefore by changing, if you can control the phase angle difference, you can control the active power flow reversely. Okay, that means you can say that P and delta, that means active power and phase angle, voltage phase angle basically, that means the phase angle difference between the voltages, sending and receiving end voltages, they have a strong coupling. Their dependence, interdependence is very strong. That means if P is changed, delta is changed. If delta is changed, P is changed. So their coupling is very strong. And reactive power flow can be changed by controlling voltage magnitude. You want to control the reactive power flow, then you can control it by reactive power by changing the voltage magnitude. Okay, that means Q and V have a strong coupling. That means interdependence between reactive power and voltage magnitude also is very strong. That means voltage control can be done by controlling the reactive power, or reactive power flow can be controlled by controlling the voltage magnitude. Coupling between PV and Q delta are weak. That means when P changes, magnitude of V is not changed much, so the coupling is weak. When Q changes, phase angle does not change much. That means the coupling between Q and delta, that is also very weak. And this feature is extensively used for power system control and as well as analysis. We'll see that when we shall talk about the power system analysis in the next semester, we'll see that this feature is extensively used. Also in power system control, this will be very much used. You'll be actually knowing this after a few classes when we shall be discussing about the frequency control. Okay. So PV and Q delta, these are weakly coupled. P delta and QV, they are very strongly coupled. And finally, you can say regarding this topic which we are discussing that active power generation has to be controlled for controlling frequency. We have seen why? Because for frequency control or frequency change, active power unbalance between the generator input and generator output, that is the responsible factor. That's why you can see that active power generation has to be controlled for controlling the frequency. For controlling system voltage, on the other hand, reactive power flow has to be controlled. We are not talking about reactive power generation here. Just observe. Why? Because we are saying about the reactive power flow through line. Because reactive power actually can be generated elsewhere also. It can be generated at the substation by installing some other devices like synchronous motor, like static var compensator, like capacitor bank, like statcom. Okay, there are so many devices available, so many arrangements available for the generation or for the control of reactive power. That's why we are not talking about reactive power generation here. Rather, we are talking about the reactive power flow. That means somehow through the transmission line, you have to limit the reactive power flow such that voltage drop does not take place greatly. Okay, there will be voltage drop, but that drop will be minimized if you can control the reactive power flow. Frequency control can be done from power plants only. This is another conclusion you can say. Why? Because for frequency control you have to control the active power generation. Okay, so if you control active power generation, where this has to be controlled? Obviously from the power plant, because active power cannot be generated outside the power plant. So at the power stations only, at the power plants only, you can actually have the facility of controlling the frequency. Okay, voltage control can be done from power stations and transmission as well as distribution substation. But on the other hand, if you want to control the voltage, this is possible from power plants and also from substation. Why for power plant? Because synchronous generator, we should see later on today itself that synchronous generator can actually generate reactive power as well. So since they can supply reactive power, they can consume reactive power. Voltage control is possible by controlling the reactive power generation or reactive power absorption by the generator from the power plants. Also, reactive power supply is possible from outside the power station. That is for transmission as well as distribution substation. Okay, you can install reactive power generator, reactive power actually consumer, okay, reactor, capacitor, all these things at the substations, both at the transmission level and distribution level. So from there also voltage control is possible. It is possible to transmit active power over long distance. Hmm. This is another conclusion we can make. Why? Because if you actually transmit active power over a long distance, then there will not be much drop in voltage. So in power system, what you have to do? You have to maintain the voltage within a specified declared level. And how much is that level? It is say 5% at the lower voltage level. It is somewhat higher at the higher voltage level. Because why higher at the voltage level? Higher voltage level because at the higher voltage level you have the more facility for reactive power control or voltage control. That's why. So since you cannot afford for the drop of large voltage, you cannot actually transmit reactive power. But active power flow does not create much voltage magnitude drop. Rather, it creates phase angle change. Phase angle change you can permit because change in phase angle also will not be very large. You see that in power system, if we consider the end buses of a transmission line at the beginning and at the end of a transmission line, phase angle difference is not very large. 4 degree, 5 degree, 7, 8 degree maybe at most, not more than that. Because if you create more phase angle difference, then heavy current will flow, and that current actually will be nearing the thermal capacity of the transmission line. That's why phase angle difference is also not much there. So active power flow, when you actually send more active power, there will be somewhat more phase angle difference, but only a very small change in when small drop in voltage will take place. But if you want to transmit reactive power, then it will create a large voltage drop. So active power may be transmitted over long distance, but reactive power cannot be done. That's why you see that people are purchasing active power from a distant generator. Okay, some several hundred kilometers it is being produced and it is transmitted over uh, the transmission line on the other side of the transmission line. It is being received. Okay, this is possible, but reactive power is never done in this way. Reactive power is never transmitted in this way because reactive power is not transportable. If you attempt to transport reactive power, then it will create a large voltage drop. That voltage drop will actually cross the permissible voltage drop limit. That's why you will not be attempting to transmit reactive power, but active power will be transmitted over long distance. Okay, so these are the issues we have to discuss in this introductory sessions. Yesterday and today I have discussed all these things. Okay, and these are the main issues for the control of voltage and frequency. You have to remember these issues not only here but later on also when we shall be performing analysis, we should be performing other control of power system. Okay, so now you, if you have anybody of you have any questions, you can make me. I can try to answer, and then I shall proceed to synchronous generator in the next slide. In the next PPT, I shall open another PPT where I shall be discussing synchronous generator. Any question from here, anybody? Bolo, anybody having any doubt, any question? Everybody could understand what was
Yes,
the content was discussed. Everybody could understand. Bolo. So I guess that because there is no response and there is no question, I assume that there is no questions from you to be asked. Okay, and you could understand whatever I wanted to tell you in this um file, in this lecture file, what was written and what was told, everything you could understand. Perhaps I have actually, I cannot remember whether I have mailed this PPT to you or not. If I have not done it, I shall be sending you today. Okay. Then let me open another file, another PPT on synchronous generator. This is regarding the basic issues of synchronous generator because we shall be discussing the voltage and frequency control as well as stability issues, and all these things are related to the synchronous generator. Voltage control is possible from the substation, power station. Already I told you that part will be discussed on the other half of this paper. I shall be discussing the frequency control, which has to be done from generator control only. I shall be discussing stability issues related to synchronous generator, and I shall also be discussing regarding the voltage control, that part only, which is possible from the generator, and that's why we shall have to discuss the synchronous generator now. Why synchronous generator? Because if you observe any power system anywhere, you'll see that almost 80% of the power generation till today is from synchronous generator, and remaining 20% is coming from renewables only. Okay, those renewables you know already that these are from solar PV, which are like DC source, and a portion is from induction generator that is connected to the wind system. Okay, so 80% of the generators in power system, in any power system, you can say now, it is from synchronous generator. That's why we shall have to discuss the synchronous generator. So basic performance, basic characteristics of synchronous generators we shall be discussing. Synchronous generators or synchronous machine will be discussed in the machine classes also. Okay, but the portion we shall be discussing here is related to its performance when it is connected to the power system. So we shall be actually considering the generator like this, as if a generator is connected to a large power system, and that power system, we shall assume that it is actually can be represented at this bus where the generator is connected, and this power system may be represented by means of this bus only, and this part is representing the whole power system, and therefore this part we shall give a name. This bus will be given a name, and that is called the infinite bus. Infinite bus. And we have a definition from infinite bus as well. Okay, what is that infinite bus? A bus which is acting as an infinite power source, which is acting as an infinite power sink, like that. Okay, infinite power source in the sense that obviously it cannot be infinite, but when we talk about a very large generator with respect to a small generator, then we can say that the capacity of the large generator, bigger generator, is as if infinite. It is very large which compared to the small generator. So we have a generator connect that we are connecting to the power system with with respect to the capacity of this generator, the capacity of the total power system is very, very large. To give you an idea regarding the relative magnitude of these capacities, say a generator of 500 megawatt capacity is being considered, that is connected to the power system. And if we talk about a large power system as the power system of India, just 1 minute. If we talk about a large power system, then what is the capacity? Indian power system has an installed capacity of nearly 370 gigawatt. 370 gigawatt. So you can imagine the difference in the capacity of the generator, of a single generator, and the capacity of the large power system. So if the capacity of our generator is 500 megawatt, obviously we can assume that 370 gigawatt is very, very large with respect to this 500 megawatt generator, so that we can consider that as if the 370 gigawatt system will be operating as an infinite capacity system. That's why we shall be referring this bus as the infinite bus. Okay, so all generators in any power system are synchronous type. Already I have mentioned that 80%, not all 80%. Induction generators are used for wind power and only a small portion from wind and solar. Generators in power system are effectively connected in parallel. So whatever you know that uh, in a power system, generators are distributed. They are not connected at a single point. They are distributed in the whole power system. And there are, if you consider the Indian power system, there are hundreds of power stations, and these stations are apart from each other. Hundreds of kilometers, tens of kilometers is the distance between individual generating stations, and effectively all these generators are connected in parallel. Okay, so we are actually talking about a generator in a group of large number of generators that are connected in parallel. Okay, with respect to a single generator, usually the capacity of a power system is very large, as I have mentioned, say 200, 300 megawatt capacity of individual generator or even 500, and there the capacity of the system is around 370 gigawatt. Hmm. It may be assumed to be infinite. So capacity of the system as if is infinite. Here, obviously, the truly, if we speak truly, it will be very large. So very large. For simplifying the discussion, we are assuming this to be infinite. So what is the property of this large capacity system, which is actually reflected in a single bus called the infinite bus? That is having a constant voltage. We assume that the generator is connected to the power system, and at this bus system voltage is fixed. In what sense it is fixed? In the sense that if you change the power output of this generator, whether the active or reactive power output of the generator is changed, the voltage magnitude of this bus will not change. Okay, that means this bus is behaving as a constant voltage source, you can say. That's why it voltage is constant. And since it is a constant voltage source, last year in the circuit theory classes, you have studied about constant voltage source. What is the property of a constant voltage source? Anybody who can tell me? Property of a constant voltage source? Last year only, you have studied about the circuit theory. In the circuit theory, you have studied constant voltage source, constant current source. So, can anybody tell me the property of constant voltage source?
That the zero internal resistance, voltage is constant.
Zero internal resistance. Yes, huh. That means the internal impedance of the source of that constant voltage source is zero, because there will not be any voltage drop inside the voltage source. Here, since we are assuming that this voltage is constant, is a constant voltage source, and since this is a constant voltage source, obviously its impedance will be zero. That's why internal impedance is zero. So property of the constant infinite bus is constant voltage source with zero impedance. Also, its frequency is constant. Why you are assuming this? Because in when we shall be controlling the frequency, we shall be applying control on this generator, and we shall assume that this generator has no capacity to change the frequency of the total. That means frequency of the total system is will remain constant, but frequency of this generator may change, and we have to control for the change in frequency of this generator only. System frequency does not depend upon the frequency of this generator. This is our assumption. So if this is the situation, constant frequency is the frequency of this bus. Obviously, a bus cannot have any frequency because a generator can have a frequency. Actually, this bus is representing the total capacity of the generator of the power system, and as if the accumulated capacity of the system, obviously this is generated by synchronous generators, that as if is represented by a single generator, and the frequency of that large generator is constant. This is what we want to mean here. So constant frequency means that generator which is representing the total capacity of the system to which this bus is connected is actually behaving as a constant frequency generator. What does it imply? It implies that this generator is having a very large and very heavy rotor. Rotor weight is rotor mass is very large. So large that by applying any force, you cannot change the speed of the generator. That means the inertia of that generator is infinite. That's why property of the infinite bus is shown to be infinite inertia. Would you understand that the infinite bus is having constant voltage, constant frequency? Constant voltage implies that impedance will be zero. That's why it is shown to be zero impedance. Constant frequency implies that its inertia will be very large. That's why we are assuming that to be infinite inertia. So these are the four properties of infinite bus. This assumption we are making for making our analysis somewhat simpler, but at the beginning we shall be assuming the system, the generator to be connected to infinite bus. Later on, when we are actually we shall learn how to analyze the system, how the we shall analyze learn to analyze the performance of the system. We shall be in a position to consider the uh, system to be finite. That means its frequency will be changing, its voltage will be changing, everything will be then taken care of. Okay. So any question here up to this? Then regarding the synchronous generator, we shall be talking about this generator that is connected to the power system, and so far we have discussed about the synchronous generator, the infinite bus to which this generator is connected. Now let us see the synchronous generator. What are the types of synchronous generator? You know that there are two types. It may be two types. One is cylindrical rotor type, another is salient pole type. And cylindrical rotor type means these generators are having actually constant air gap, uniform air gap. These generators are high speed generator. They have small diameter, they have long rotor, and number of poles are small in number. Number of poles are small, and speed is very high. So their construction is very rugged. Okay, their air gap is uniform, and generally these type of generators are used in thermal power plants, because thermal power plants, the turbine that are used in thermal power plant, they run efficiently at high speed. Okay, all right. And uh, a synchronous generator, because they can run at very high speed, because of their rugged construction, they can be moved at very high speed. That's why they are connected at thermal power station. They are using thermal power stations, and the turbine used are steam turbine. They run efficiently at high speed. That's all. And salient pole machines, they are having salient pole. That means pole can be seen, can be located from outside. By observing the machine, you can say that these are the poles. Okay, for cylindrical rotor machine, this is not so obvious. Poles are not projected, but for salient pole machine, poles are projected pole. And projected pole means poles are surrounding the machine. Okay, and the circular is the cylindrical is the shape, so poles are observable, and between poles, the air gap obviously will not be same as the air gap in front of the pole. So projected poles unequal air gap. Since air gaps are not equal, reluctance of the magnetic circuit measured at the pole face and away from the pole face, obviously this will be different. Okay, different reactance, different reluctance. Different reluctance means obviously, therefore the reactance also will be different. That's why this type of machine, salient pole type machines, their analysis is somewhat more complicated than the analysis of the cylindrical rotor type machines. Okay, and they are having, since their air gap is projected, and they are having short rotor and large diameter, large number of poles may be there, and their speed is rather low because projected pole, these machines are not that rugged. You cannot run this machine at very high speed. So, since you cannot run these machines at very high speed, to create required capacity, obviously large number of poles will be needed. That's why their diameter are large. A large number of pole can be housed in that diameter, in that space. Okay, and their rotor is rather short. And these type of machines are used in hydroelectric power plants, because hydroelectric power plants, the turbine used, hydel turbine, they run efficiently at low speed. Okay, so, and these machines are all low speed machines. Therefore, they are used in hydel power plants where the turbine used, they work more efficiently at lower speed. So these are the types of the machines we shall be discussing and we are having. But for convenience of our discussion, for simplicity of discussion, we shall be assuming that our machines are all cylindrical rotor type. Why we shall assume this? Because this will make our analysis somewhat simpler, because cylindrical rotor machines are having uniform air gap. That means reluctance is same everywhere in the magnetic circuit. Since the reluctance is same, you can represent this machine by a single reactance. That is, in the equivalent circuit, you can show a single reactance to represent the machine impedance. Okay, this will simplify our analysis. That's why, to begin with, we shall assume our machines to be all cylindrical rotor type. But later on, when we complete the discussion on cylindrical rotor machine, we shall be introducing the salient pole type also. We shall show how the analysis of the salient pole machine differs from the analysis of the cylindrical rotor type machine. That also we shall be discussing. Okay, so to start with, we shall assume our generator to be cylindrical rotor type. Okay, now let us uh, start with the phasor diagram. From phasor diagram, we shall be drawing the equivalent circuit, and then we shall be writing the power equations. For power equation, we shall see how to control the active and reactive power, because our aim is to control the frequency and voltage. For frequency control, active power control is necessary. For voltage control, reactive power control is necessary. Okay, so let us see the phasor diagrams. The construction of synchronous machine, it has an armature winding, three-phase armature winding, which is on the stator, and rotor is a DC winding. Rotor carries DC current, okay, direct current. So it, that means the field current is direct, is DC, and armature is situated on the stator. Why armature is on the stator and field winding is on the rotor? Because field winding, its power capacity is less, so it has to handle small current, but armature winding, its power capacity is large. It has to handle large current. Collecting current for outer circuit from a static winding is easier than collecting it from a rotating winding. That's why this armature is on the stator and the field winding is on the rotor. Okay, so you have a field winding and current is flowing through that winding. When the current is flowing through the winding, obviously a flux will be created. Let us assume that this direct axis shown here is the physical direct axis of the pole also. This is as if the pole is lying on this axis and the winding is made on the pole. Direct current is flowing. So if you actually uh, are having the, if you put your fingers in the direction of the current around the winding where the current is flowing, and obviously the thumb will uh, direct the represent the direction of the flux created. So this is the direction of the flux, IF, direction of the flux that is created because of the flow of field current in the pole winding. Okay, so if this is the direction of the flux, the induced EMF in the armature, the pole will be rotating at synchronous speed. Obviously, the pole will be rotated by the prime mover. Prime mover here is the turbine. Okay, thermal steam turbine is the prime mover. It will rotate the pole winding or machine rotor at synchronous speed, say. So as a result, the flux is there, it is rotating, so there is a rate of change of flux created. It is linking with the armature winding, and the armature, in the armature EMF will be induced, and that EMF is represented by this phasor. Obviously, phase angle difference between the field flux and the induced EMF will be 90 degree. So if this is the direct axis or pole axis of the rotor, then this is along the EF is along the quadrature axis. That means shifted by 90 degree with the pole axis is the quadrature axis. So EF, induced EMF, will be along the quadrature axis of the rotor. Okay. Let us assume that if this is the induced EMF, say terminal voltage is somewhere here. We are assuming this for the time being. We are assuming that terminal voltage is lagging the induced EMF, say by angle delta. Okay. Why we are assuming that? Because generator will deliver active power, and active power always flows from a leading vector to a lagging vector. Already I have mentioned that I am talking about the generation system here where the resistance is very small. Then here you will see that active power will flow from induced EMF from a leading vector to the lagging vector. So if this is the direction of the induced EMF, terminal voltage will lag it by some angle. Say that angle we are giving it a name. Say that is delta. Okay, and say the load that is being supplied by the generator is lagging. Because in power system, the power factor of the load is generally lagging. There are almost very few loads that are actually that will operate at leading power factor. The most of the loads are lagging power factor loads. So armature current IA that will lag this terminal voltage, say by some angle. This is the direction of the armature current. So if this is the armature current, because of this armature current, there will be a armature flux created phi A. This armature flux phi A will interact with the field flux because in the same air gap they are existing. So they will have the interaction. As a result, phi R is the resultant flux. That means phi R is the resultant flux of phi f and phi a. Phi f is the field flux, that means flux created by the field current. Phi a is the armature flux, that means the flux created by the armature current, and phi r is the resultant flux. So if this is a resultant flux, resultant voltage, that means the terminal voltage will lag this flux by 90 degree. That's why this is Vt. Okay, previously I told you that Vt is lagging this by some angle delta, and I have shown Vt here. But now you see the reason for that. That this is fire and Vt will lag this fire by 90 degree. Okay, so this is EF, this is Vt, and why there is a difference between EF and Vt? Because of the drop in the machine reactance, machine impedance. In the machine impedance, we are neglecting resistance because resistance generally is very small with respect to the inductive reactance for a generator. So that resistance is neglected. For simplicity also, we are neglecting that small resistance here. So if Ia is here, JIA into reactance, it will be 90 degree with Ia. Okay, so that is 90 degree with Ia. So this vector is J, that means leading Ia by 90 degree, J Ia into XS. XS is the synchronous reactance. Synchronous reactance means reactance of the synchronous generator or synchronous machine when the machine operates at synchronous speed. At steady state, machine will operate at synchronous speed. That's why the reactance that it will offer to the flow of current will be referred to as the synchronous reactance. This synchronous reactance, why this is actually appearing? This is appearing because partly because of this phi A, armature reaction flux, and that component of reaction is XA, armature reaction reactance. There is another component which is not linking with the, which is not interacting with the field flux. That is the leakage flux of the armature winding. Okay, that is leakage flux. So that also will create a voltage drop. You can say effectively there is a voltage drop, and that part of reactance is say XL. So XL is the leakage reactance, and XA is the armature reaction reactance. The corresponding flux is phi A. Corresponding flux of XA is IA, and corresponding flux of XL is the leakage flux. That is not being shown here because that is not interacting with the field flux. Okay, so this therefore is the phasor diagram of the synchronous generator. Okay, delta is the angle difference between the induced EMF and the terminal voltage. This delta is sometimes called power angle. It is also called the load angle, or sometimes it is also written as or referred to as the torque angle. So torque angle, power angle, load angle, it has different names, and that angle, that is basically the angle between the induced EMF and terminal voltage. Okay, so this is the phasor diagram. If this is understood by everyone, then we shall proceed to develop equivalent circuit of this machine. So please tell me whether all of you could understand the phasor diagram of this machine. This is the phasor diagram of cylindrical rotor machine because we are talking about single reactance, synchronous reactance. Okay, synchronous machines will have other type of reactances also, like transient reactance, subtransient reactance, when the machine speed is not synchronous. Okay, we shall be talking about those reactances later on when we shall study stability. Then we shall be talking about the synchronous transient reactance as well as subtransient reactance. But now we are talking about the steady state performance of the synchronous machine. Obviously, we shall be talking about the um, frequency control. During frequency control, there will be some deviation of the machine speed from synchronous, but that deviation is generally very small so that we can neglect that speed change. That's why we shall assume that the synchronous reactance uh, it will be applicable for the analysis of frequency control as well. Okay. Any question? Could you understand the discussions what I have made here regarding the phasor diagram of cylindrical rotor type synchronous generator? Remember that EF is leading here by Vt by an angle delta. This is the phasor diagram of generator. For generator, power flows from the machine to the terminal. That's why EF is leading Vt. When we shall be talking about the motor, direction of power is just reverse. Power will flow from the machine terminal to the from the supply to the machine. That's why it will flow from terminal voltage to the induced EMF. Okay, the terminal voltage will then lead the induced voltage. Here, in case of generator, terminal voltage is lagging the induced voltage. Any question? বলো, কারো কোনো কোশ্চেন রয়েছে, কারো কোনো ডাউট আছে? Anybody, any question or any doubt? If there is no doubt, then concentrate on this part of the phasor diagram. This part, electrical portion. Okay, you see that this part, phi F, phi A, and phi R. These three are related to the magnetic circuit. These are the flux. Okay, and EF, BT, and IA. These are the electrical quantities along with JIA axis. These are the electrical quantities. So these will be required for drawing the equivalent circuit of the machine. Hmm. Also, please note that this EF is along the quadrature axis of the rotor. This is very important to it will be very important when we shall be studying frequency control. We should be turning change in power generated by generator everything. Okay, EF is along the that means induced EMF is along the quadrature axis of the rotor. That means if you want to change the delta, we said that by changing delta, active power flow can be changed. If you want to change the value of delta, then position of EF with respect to Vt has to be changed. Now, note that Vt is representing the infinite bus voltage. Infinite bus voltage, obviously, this is an alternating voltage, so it has a frequency. What is the frequency? That frequency is constant, that is the synchronous frequency. So, Vt is rotating at synchronous frequency. That means angular speed of Vt is synchronous. At steady state, EF is also rotating at synchronous speed. EF is the induced voltage. Synchronous machine, when it generates, obviously it will be generating at synchronous frequency. So frequency of EF also is synchronous. Angular speed of EF is synchronous. So both EF and Vt, they are rotating at synchronous speed. All right. And at steady state, this angle delta is constant. All right. And EF is along the quadrature axis of the rotor. So if you want to change the value of delta, or you say that if there is a change in the power generator generated by the machine suddenly, okay, then what will happen? Then obviously the speed of the machine will deviate from synchronous, and in that case, there will be a change in the value of delta. Okay, because change in speed means with respect to Vt, position of EF will change because Vt always rotates at synchronous speed, and EF, since it is rotating at with the rotor, okay, its position will vary along with the variation of speed of the rotor. If the rotor rotates at its speed which is above synchronous, then EF will move away from Vt. If EF If rotor rotates at a speed below synchronous, then what will happen? EF will come closer to Vt. Okay, so remember this position, note this issue, it will be recorded later on. Okay, now after I told you to observe this portion only, this part of the equivalent circuit only. From here, we shall be drawing this equivalent circuit. Equivalent circuit, here you see that in the equivalent circuit we are showing EF at an angle of delta, Vt at angle of 0. This is the generated voltage EF, and this creates a phase angle difference of delta with respect to terminal voltage. Terminal voltage angle is shown to be 0 degree because we are using the terminal voltage as the reference phasor. It means phase angle will be measured with respect to the terminal voltage, and induced EMF is leading the terminal voltage by an angle delta. That's why induced EMF is EF at an angle of delta. Machine, there is a drop of JIA excess. To represent that, we have shown the reactance here excess. Obviously, it is J excess, okay, and the current flowing is IA. So JIA excess is the drop here. Okay, so this is the equivalent circuit, and this equivalent circuit has been drawn using this part of the phasor diagram. That means the electrical part of the phasor diagram. Current flowing is IA, that is shown. Terminal voltage is shown. It is used taken as reference. Induced EMF is shown. It is making an angle delta with respect to terminal voltage, and this drop is JIA excess. This is being created by this current when it flows through this reactance. Okay, all right. Now from this equivalent circuit, now you can have this expression for current that is flowing. What is the current? How much is the current flow? You see that current is given by this voltage minus this voltage by Jxs. EF at an angle of delta minus Vt at an angle of 0. This voltage minus this voltage by this reactance Jxs. J is not written here, but actually it will be Jxs. Note that this current Ia, this is the complex current. It has some angle, but it is a complex current. We are not showing any angle here. But remember that this is complex current. So Ia is EF at an angle of delta minus Vt at an angle of 0 divided by Jxs. Okay. So from this, we can write the expression for power delivered by this generator. How much is the power delivered by this generator? It will be that means this is the generator terminal. How much is the power going out of this terminal? It is P plus jQ. And what is the expression for P plus jQ? It is the voltage into conjugate of current, V T at an angle of 0 into I conjugate, means IA conjugate. Okay, you put the value of IA here, it is EF at an angle of Vt minus Vt at an angle of 0 divided by Jxs. So it is Vt EF at an angle of minus delta because of conjugate delta is becoming negative here, because when you take the conjugate, this will be negative JIA, Jxs will be minus Jxs, and Vt at an angle of 0, so its conjugate is Vt only, so Vt square. So P plus jQ becomes Vt EF at an angle of minus delta minus Vt square by minus Jxs. Okay. What is the real part? You take the real part of this, that will be equated to P. P becomes EF Vt by Xs sine delta, and imaginary part is Q. Q becomes equal to Vt by Xs EF cosine delta minus Vt. Take the imaginary part, J part of this expression, then it will be Vt by Xs EF cosine delta minus Vt. Alright, so this is the expression for active power delivered by the machine. Note that the expression we have developed here of power P plus jQ, we are talking about the power delivered by the machine. It is both the active power is being delivered and as if the reactive power also is being delivered. So P positive means power is being delivered by the machine. Q positive means reactive power is being delivered by the machine. If sometimes we find that P and Q or any one of these becomes negative, then obviously that power will represent the power being consumed by the machine. Okay, if Q becomes negative, it will indicate that reactive power is being consumed by the machine. So, power delivered is positive here, and that is EF Vt by Xs sine delta for active power, and for reactive power Vt by Xs EF cosine delta minus Vt. All right. Any question up to this? Now, how to how to control this power? We shall now talk about how to control the active power and how to control the reactive power. Then we shall stop today, and other issues we shall discuss in our next class. Okay. So you see that P active power is given by P equal to P maximum sine delta. We have written this. That means EF Bt by Xs that we are writing as P maximum. Why we are writing this as P maximum? Because this is representing a sine curve. EF Bt by Xs sine delta, it is representing a sine curve like this. Okay, and this is as delta varies, obviously power generated also will vary. What is the maximum amount of power that is possible from this that we can get from this machine? That is obviously this part here Vt by Xs, so that's why it is written as P maximum. So you see that EF is the induced EMF. So if we assume that the field current is constant, we are not controlling the field current, we are not changing the field current, then obviously EF will be constant. Vt is representing the infinite bus voltage. That is a constant voltage. So EF is constant, Vt is also constant. Excess synchronous reactance, obviously that is also constant because that depends upon the machine. When the machine is constructed, when the machine is designed and constructed, obviously excess is constant. Okay, so if the field current is kept fixed, then EF Vt by Xs is constant. That means active power will vary according to the sine curve. Its maximum value is P maximum given by EF Vt by Xs. Okay, so if it is kept fixed, how can you vary the power delivered? Because you have to control the frequency, you have to control the vary the active power output of the generator, and how the active power generated may be varied by varying delta, by varying the angle delta. Okay, and how delta can be varied? You see, that's why I told you to note this angle delta. How delta can be varied? Obviously, by varying the speed of the generator. Momentarily, you have to change the speed of the generator. How the change of how the speed of the generator may be varied? Obviously, by changing the power input to the turbine. That means turbine power input has to be varied. What is the turbine power input for steam turbine? That means the turbine used in thermal power station, which is the steam turbine, and steam is the input to the turbine. That means opening of the turbine valve has to be changed for changing the power generated by the machine. That means turbine torque turbine output to be varied by obviously by varying the turbine input. Turbine output goes to the generator. Then generator input has to be changed. For changing the generator input, turbine output has to be changed. For changing the generator output, turbine input has to be changed. And what is the turbine input? That is nothing but the steam. Steam comes from boiler through the um, steam valve. That means steam flow rate has to be changed. How? By changing the opening of the steam valve. So if you want delta or if you want P to be larger, then increase the opening of the steam valve. If you want to reduce the power generation, reduce the opening of the steam valve. Okay, could you understand? That means for changing the active power output, it is the opening of the steam valve that has to be changed. For increased power output, opening of the steam valve has to be increased. For decreased power output, opening of the steam valve has to be decreased. Okay. Now, note this sine curve, or also called the power angle curve, angle beta, because this is the curve representing the power generated, power output, and the angle, phase angle delta. That's why it is also called the power angle curve. To note this power angle curve, 90 degrees is the maximum position of this curve. That means here the maximum power is generated. Maximum power generated is represented at this point. Right side of this delta degree, that means this portion represents unstable operating zone of the machine. Left side of this position represents the stable operation zone. Why this is unstable zone, why this is stable zone, I shall be explaining later on, but that requires some response from you also. Otherwise, if you do not understand, there is no meaning of discussing all these things. So I shall not be discussing this part today, because I want that when I send you that file, you will be going through it, you will be thinking about this, and then in the next class I should be discussing about the significance of this unstable and stable operating zone, why this part is stable and why this part is unstable. So before that, let me discuss regarding the control of reactive power. We shall be assuming that reactive power has to be controlled by keeping the active power output constant. The turbine output is kept constant because if you change the turbine output, then active power will change. So we should assume that we are not changing the turbine output. That means steam valve opening is kept constant. Okay, so P remains constant. Then how to control the reactive power output? So look at this expression. It is EF Vt by Xs. Vt is constant. Okay, terminal voltage is constant, infinite bus voltage. So EF cosine delta minus Vt. Obviously now delta and cosine delta and EF may be changed. How EF may be changed? For changing the EF, what has to be done? Obviously, field current has to be changed. That means if somehow we can change this product EF cosine delta, then reactive power output may be changed. It may be increased if EF cosine delta is increased. If you want to decrease it, then EF cosine delta has to be decreased. If you make EF cosine delta greater than Vt, then Q will be positive. If you make EF cosine delta less than Vt, then EF will be negative. Or even EF cosine delta, it may be possible to make equal to Vt only. In that case, Q will be 0. So now you come here and see this phasor diagram. We have drawn three phasor diagram here. There is some error here. It should have been written IA3, IA1, and IA2. Rather, they have written IF. These are not representing the field current. These are representing the armature current, because these are showing the armature current, and these are the JIA axis, armature reactance drop. Okay. So there are we are keeping P constant. P constant means, you see that P constant means this portion is constant. If Vt by Xs is always constant because we are not changing the field current, say. Now P maximum sine delta this portion will remain unchanged. That means somehow sine delta, P maximum sine delta, that is EF BT by X sine delta, this part has to be kept constant. Okay, EF sine delta part has to be kept constant. So we shall be changing EF cosine delta, but EF sine delta part has to be changed, has to be kept constant. Obviously, there will be some variation in delta, there will be some variation in EF, but EF sine delta, this part will be kept constant. So if this part is kept constant means this perpendicular portion is kept constant. Now, if this is if you want to change, keep this perpendicular part constant but change EF cosine delta, obviously that is possible by changing the field current. So if you send, or if you increase field current, then EF will increase. If you reduce field current, then EF will decrease. So at increased field current, we are getting EF2 because length of this vector is larger than this length. So from EF1, EF2 is larger. From EF3, EF1 is larger. But in all the cases, the EF sine delta, this component, that means the projection of this phasor on VT, this perpendicular length is constant, this perpendicular length is constant, this perpendicular length is constant. Okay. So EF2 is greater than EF1, EF1 is greater than EF3, means field current here is greater than the field current here, is greater than the field current here. These phasors are not IF3, IF1 or IF2. They are actually IA3, IA1 and IA2. Wrongly they are written IF3, IF1 and IF2. Okay. So for this phasor diagram, say EF1, terminal voltage is fixed always, infinite bus voltage VT, then it is JIAX, IA1 excess, we are getting EF1. For this one, it is VT, then JIA 2x excess, JIA2, that means 90 degree with this is the direction of IA2, and we are getting EF2. This is EF3, so VT plus JIA3 excess. So direction of IA3 is this one. Okay, so you see that now in this case, EF2 cosine delta is this much, horizontal portion. This is greater than VT. For this EF1 cosine delta is this much, equal to VT. For this EF3 cosine delta is this much, it is less than VT. That means EF cosine delta minus VT, it will be negative here. EF cosine delta minus VT will be positive here. EF cosine delta minus VT will be 0 here. That means Q may be changed if EF cosine delta can be changed. And how EF cosine delta can be changed? Obviously by changing the field current. So by changing the field current, it is possible to change the generated voltage. By changing the generated voltage, you can change the reactive power output of the generator. Alright, note that when induced EMF is larger for constant active power generation, we are talking about constant active power generation with varying reactive power generation. For constant active power generation, if induced EMF is having larger magnitude, delta is having a smaller value. So delta in case of EF2 is smaller than delta in case of EF1. Similarly, delta in case of EF1 is larger than delta in case of EF3. So smaller the induced EMF, larger is the value of delta. Smaller the induced EMF between these two, larger is the value of delta. Delta 2 is larger than delta 1. Delta 3 is larger than delta 2. EF3 is smaller than EF1. EF1 is smaller than EF2. Okay. So EF cosine delta, this horizontal part for the projection, this is being changed, and this is being changed by keeping EF sine delta, this component fixed. All right. That means field current is being changed, and by changing the field current, reactive power generation of the synchronous generator may be changed. All right. So up to this, if you have any question, you can ask me. In the next class, I shall be discussing the remaining portion, including this stable and unstable part. Why this is stable and unstable? But this requires some thinking on your part. This requires some involvement from your part. For that, I shall be sending you this PPT. Go through this, observe this, think about this. Then we shall be in a position to discuss further. Now, any question from your end? If anybody is having any question, you can make me. Otherwise, I will close the session here. I shall make a roll call and then I shall close. বলো, কারো কোনো প্রশ্ন আছে? কারো কোনো প্রশ্ন আছে? কারো কোনো প্রশ্ন নেই? গুড। তাহলে দেখা যাক কারা রয়েছে।
স্যার এই নোটগুলো পাঠিয়ে দিবেন।
না, নোট পাঠাবো। নোট তো তুমি বই খুললে নোটের ছড়াছড়ি। বইয়ে আমার এই যা নোট আছে তার 100 গুণ নোট বইতে পেয়ে যাবে। কিন্তু বুঝতে হবে ব্যাপারগুলি। তোমাদের কোনো রেসপন্স দেখে তো রেসপন্স জিরো, কাজে বোঝা মুশকিল যে বুঝতে পারছো কি পারছো না। নোট পাঠিয়ে দেব, পরীক্ষা হবে, সবই হবে, কিন্তু বোঝা না হলে কোনোটাই কোনো কাজে লাগবে না। কিছু নম্বর পাবে, সেই নম্বরটার কোনো ভ্যালু থাকবে না। বুঝতে পেরেছো? ঠিক আছে। অভিজিৎ দাস,
Yes, sir.
আবিদ হাসান,
Present, sir.
আবিদ হাসান, আবু সৈয়দ
স্যার
শেখ,
আবিদ হাসান, আমার
আবু
নেটওয়ার্ক
সৈয়দ,
Yes, sir.
উইক আছে। হ্যালো
Yes, sir.
আবিদ হাসান। ওকে ওকে, অলরাইট। অহন বসু, অহন বাসু, অহন বাসু। হ্যাঁ, তাহলে তুমি পাঠিয়ে দেবে, যেটা তুমি রেকর্ড করলে পাঠিয়ে দেবে। আকাশ সিংহ রায়,
Yes, sir. Present.
আকাশ।
Yes, sir.
অগ্নিব চ্যাটার্জি কি এখন মাত্র ঢুকলে? কি অগ্নিব চ্যাটার্জি মনে হচ্ছে এখন ঢুকলে?